to the beginning here. Okay. Now, this looks awful weird, and you may not share my enthusiasm, but the question is, what does the derivative of the absolute value function have in common with this expression right here? Now, this is just a function. This is just a function, e to the 1 over x over 1 plus over the quantity 1 plus e to the 1 over x. So over here, we're talking about a function defined by the derivative, and over here, we're just talking about a function. So this is very open-ended, obviously, and there's a lot of things probably it has in common, but there's one thing in particular that's of interest to some of us. All right. Now, so let's get busy with the absolute value. I like this definition of absolute value. In fact, I call it the continuous version of the absolute value definition. This is piecewise. It's discrete if you want to call it that, but this is a piecewise definition. But this definition of absolute value is actually useful in many instances, sometimes when you're working with absolute value equations. And also, it's a seamless way to determine the derivative. Now, just to be sure here, let's say a was equal to -4. The absolute value of -4 is 4. The -4 squared is 16 squared is 16 is 4. So it's pretty clear that this continuous looking version is equivalent to this piecewise discrete version. Now, so it gives us a nice way to find sort of a closed form for the derivative of the absolute value. So if you do d dx of the absolute value of x, replace it with what it's equal to right here, right? And then we can employ the chain rule. You see we have a discernible outer function, the squared function, and an inner function, x squared. So all of this is the chain rule going on. And then at the very end, remember the square root of x squared is the absolute value of x, so we get x over absolute value of x. Okay. Now, so we see at this point that just like this function, notice that 0 is not in the domain of this function here, 0, because you would have e to the 1 over 0, division by 0 is undefined. Well, right here, obviously, we would have 0 in this function. So one of the very first things to note is that they share the same domain, which would be minus infinity to 0, union 0 to infinity, kind of a long-winded way of saying exclude all real numbers except 0. But anyway, and that also indicates that neither one of them could be continuous at x equals 0. Now, just a word about what this graph would look like. As long as x is positive, this is just going to be equal to 1, right? But let's say if x were equal to -3, let me just go ahead and see if I can do something here. Whoops. Okay, I can't. Oh, there we go. I'm just trying to use this. Yeah, here we go. So let's say that x were equal to -3, then you would get a -3 right here. Okay, divided by the absolute value of -3, right? Okay, it's working out better than I thought it would. Okay, but notice that is equal to -1. And that is equal to -1. Now, again, I don't need to show you the example. If x were 3, then you just have 3 over 3 and it's equal to 1. So to the right of 0, the graph of the function is going to be just a constant value of 1, and to the left of 0, the graph will be -1. Now let me clear all this out here, and so let's move along and take a look at the graph. Okay, now so here's the graph, and this is more or less a picture of what I was just saying. And so there is a jump discontinuity at x equals 0. And notice this wasn't any kind of contrived sort of thing. It came from a continuous definition of absolute value. Okay, so you get something that appears in nature, so to speak. All right. Now, now let's go ahead and investigate what goes on with the other function. Okay. Now we're not taking the derivative of this. We're just trying to find out what it has in common with the derivative of the absolute value. All right. So now one way to look at this without having to, I think Michael Penn did this using a U substitution or something. I think it's easier just to remember that what this graph looks like. 1 over x, as x approaches 0 from the right, this is the reciprocal function. It certainly approaches infinity. And so what you would be getting right here is e to the infinity. So this is in the form e to the infinity. I mean, it's in the form infinity over infinity. It's indeterminate. You could use L'Hopital's maybe. But a trick right here, it's kind of like the rational function trick where you divide through by the highest power of x to get a lot of stuff to go to 0. I divided everything in sight by e to the raised to the 1 over x. So you get 1 in the numerator, you get 1 over e to the 1 over x here, and then you get 1 there when you do it. Again, y'all, I divided everything in sight by e to the 1 over x. Numerator here, and this is what resulted. Now, so you can see right here, now you have, again, using this truth, you would have e to the infinity. So this would be the only piece, this, oh good, that worked. That goes to 0, so you get 1 over 1, all right? Now, it turns out, and I scratched my head quite a long time on this one, this same trick doesn't really work when you look at the left-hand limit. Notice this was the right-hand limit here, folks. This is the right-hand limit right here that we're talking about. Okay, right-hand limit, that piece right there. Now we're talking about the left-hand limit right here, all right? Now, it turns out it's just easier to examine this all by itself, you know, without doing any tricks to it. As x approaches 0 from the left, 1 over x approaches minus infinity. That's easy to see if you're familiar with the graph of the reciprocal function or just substituting numbers in there. But if you think of e to the minus infinity, that this graph, the e to the x function, the exponential function, has a horizontal asymptote of 0, right? For quote large negative values. So e to the minus infinity is equal to 0. E to the minus infinity, it's a bad way of saying it, but it's the truth. It's equal to 0. So this is all equal to 0. So what we have here is a left-hand limit that's equal to, excuse me, we have a left-hand limit that's equal to 0, and then a right-hand limit that's equal to 1. So they disagree. That means they also have to have a jump discontinuity. And let's go to the next screen here. And there we go. And I summarized it right here. This function, like ddx of the absolute value of x, has a jump discontinuity at x equals 0, and you can see it here. Y'all, I didn't graph this by hand. It turns out also it's a horizontal asymptote going here, which is kind of cool. But when Dr. Penn did this, he was trying to say, come up with another function that appears in nature, all right? Now, he said that tongue-in-cheek, quote unquote, but this appears in nature. It's not some kind of contrived piecewise function. Like in most calculus textbooks, that's how they do this. They'll define, like, say, let the function be equal to 4 for x to the right of 2. Let the function be equal to 1 for x to the left of 2, and you're naturally going to have a jump discontinuity at 2, but it had to be designed, it had to be built up and propped up by a contrived piecewise function. These are so-called natural functions, although whatever that means, you know, they're just, you know, but in any event, that was the point of this whole exercise. I hope you stayed awake during all of this. Both of these functions had jump discontinuities without requiring a piecewise definition. Now, if anybody paid careful attention to this, the absolute value is a piecewise function, right? But I didn't use that version, but I used this continuous version. So there you go. And to me, the most meaty part of this video was actually being able to get a clean closed form definition for the absolute value, the derivative of the absolute value function, using the chain rule and this definition. All right, hope you guys enjoy.